you ready to start? How many of you are familiar with something known as the traveling salesman problem? Traveling salesman problem. 1, 2, 3 and a half. So, traveling salesman. You know what a salesman is? Okay, that's a good start. You know what traveling means? Okay. So we're 50% there. Traveling salesman has to go from place to place. And so, let's say we are going to have a few target locations. So we're going to send our salesman to maybe a few places across the city. Or maybe a few cities, I don't know. And so what we're going to have is, these are all the different places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are all the places where the salesman has to visit. And so, in this case, we have the number of cities, n is equal to 10. And we will allow the salesperson to start any place they want to. So maybe they're already here, so they're going to start from here. Or maybe they're here, they can start from there. And the idea is that the salesman has to start or saleswoman, right? But it's called traveling salesman problem. I never heard it called the traveling saleswoman problem. You could have traveling salesperson. But when I say salesman, it could be anybody. So the idea, so the idea is that we can start anywhere, but now we have to go to every other place. So there are 10 locations, but if we start at 1, we really have only 9 locations to go to. Okay. And so therefore, we have a choice. From here, maybe we choose to go here. Once we go here, we cannot come back here again. So from here, we have to add another new place. Maybe we go here, maybe we go here. So we're going to choose some next locations. So what we're going to do is, if we have a sequence of numbers, and the sequence of numbers is 1, 2, 3, all the way up to 10, the order that we're going to visit the cities ends up being a permutation or an ordering of the 10 digits. Now, if I allow myself to start anywhere, that becomes another choice. So if I can start anywhere, here or here or here, the first one is going to, so the first place I'm going to start is going to be a number, 1 through 10. Followed by another number, not the same one as before, followed by another number, not the same as the previous two, followed again, 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 again. So what I will end up doing is I will end up with having a permutation of the first 10 numbers. So therefore, the number of what we call cycles to visit everything, it's going to be, in our case, it's going to be n factorial, or in our special case, it's going to be 10 factorial. And 10 factorial is a rather surprisingly large number. It's approximately equal to about 3.6 million. So 10 times 9 times 8 times 7, it goes up to so quickly. So you can imagine 11 factorial would be over 36 million, because it would be 11 times that, so it's at least 10 times that, but another, so 30, so it would be 36 plus another 3, so it's almost 40 million. And then 12, 400 million, then we get into the billions. So it grows very, very quickly. So we would like to find the best way to do it. So we can think about solving an algorithm, but what would an algorithm look like? How would you find the shortest path? Because we assume that each of these locations has an xy coordinate, so we can measure distance between any two. So if I put a particular sequence, then I can go to, so a sequence is going to be something like, you know, I'm just going to come up with a random one. So let's say 5, 4, 1, 8, 7, 2, 6. It's getting harder because I can't replicate any, right? 6, and then I'm going to go, let's say 3, 10. What am I missing? 9?
9.
Wow. You get A+ for being very tuned in. Okay, so that's a solution, right? Is it the best solution? I don't know. First of all, I have no way of testing it because I don't have numbers here. Of course, I can add numbers here, right, if I want to. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5 to 4, I can't read my own writing, but I'm going to say this looks like a 5. So 5 to 4 would be basically this direction, right? 4 to 1 would be this one. So everyone, so I could, now of course, the implication is I have to come back to the original place. And to come back to the original place, the 9 has to come back to 5. And that makes a whole cycle. So that we are going to create a cycle. Now, what I'm going to have is I'm going to have another matrix here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each of them is going to have an ij value, where the ij value will be the distance I go from I to j. So if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and my first move is 5 to 4, I go to row 5, column 4, I find out the value, and that's going to be my distance. And then I go from 4 to 1, so I go 4 to 1 and get that distance, I keep accumulating them. The last one I'm going to go 9 to 5, so I'm going to go 9 to 5, get that one, add it, and when I have that, I have my distance. Now the question is it the best distance? Is it the smallest distance I can have? Because the goal of TSP, Traveling Salesman Problem, TSP, Traveling Salesman Problem, is to have the smallest distance. Because a salesman wants to have the most time talking to you, convincing you that you should buy his stuff, or her stuff, and smallest amount of time walking, driving, whatever we have to do to get there. So we want to minimize the distance. So this is a possible solution, one permutation of the numbers 1 through 10. Is it the optimal solution? What do you think is the probability of that?
Very low.
Well, knowing that I pretty much came up with this randomly, or randomly, you would guess I don't have a very good, if there is one best solution, my probability of that being the best solution is 1 out of 3.6 million. And those are not good odds. If somebody told you have a 1 out of 6 million, 1 out of 3.6 million probability of crossing the street without getting hit by a car, you're probably staying on that side of the street. You're not crossing today. Because your probability of getting hit is 1 minus 1 over 3.6 million, which is 0.9999999, and then maybe we'll get a 6. So for all intents and purposes, you're going to get hit by a car. You might not, but the probability is so low, I don't think you want to take it. So the probability, this is the best solution, is very, very small. Could it be the best solution? Absolutely. Absolutely. Is it? Probably not. I can almost certainly, I would bet a lot on that this is not the best solution. Because the odds are with me, big time. So, the question is, if this is not the best solution, how do I find the best solution? What is the algorithm to get me the best solution? Because the best solution would have to be better than any other solution. So what would be an approach that I could do to try to solve this? How would you approach finding the best solution?
Shortest distance between the two.
So I have the distance matrix. Distance matrix is 10 by 10. So I have that, but I'm using it right now to gauge the quality of this. Because this means nothing until I see how far is this, right? And this, and this, and this, and this, all these, and this, to here. So I need to find the best solution. So how will I know it's the best solution?
Shortest distance between the two paths should be preferred.
Shortest distance between the 2 points.
Points.
Well, that's what I'm trying to find. But what I'm saying is, how do I know that I have the best one? So I'm going to say, I think this is the best one. How can you prove that it's not? How can you prove that it is? How can you show that this solution is not a best solution? What would you have to do to show that?
Identifying a smaller
Who's sucking? Yeah, so we'd have to find another sequence that had a shorter one, right? How many do I have to search for? 1 minus 10 factorial left, which is a lot, right? Now what if the one I found by accident was not the best, but it was the second best? Then I would be trying to find all the other ones. Might take me a very long time to find the one that's actually best. Oh, I guess it's not the best. I found one that's less. Now, show me that that one is the best. Well, to do that, you have to show that all 1 minus 1 minus 10 factorial are higher or no lower. So, what will be the complexity of that algorithm? Showing that a solution is, how about if I could prove that something is the best? I found the best solution, I want to prove it. So how would I prove that? I could prove it if I were to show that every other path is, there's no path that is shorter. Okay, if I could prove that there's no path that is shorter, that is the shortest path. But I can only prove it if it were true. And in order to find the shortest path, I think I would have to investigate every single path. Because if I don't investigate every single path, then maybe the one I didn't investigate is the best one, and how could I be sure that mine is the best if I didn't test it against every other one? So therefore, the cost of evaluating n factorial paths has to have a cost of n factorial times the cost of evaluating a path, which I think is pretty cheap. I think finding the path is most difficult. Not most difficult, but there are the most possible choices. Are you with me? Does that make sense? Okay, so now what I want to know is is it possible to run a computer? Is it possible to run a computer and determine that we have the best path or find the best path when n is equal to 10? That's the question. Well, I happen to have something in my hand, which is very nice. It's called an iPhone. And what I'm going to do is I'm going to type in 10 factorial, which gives me 3.6,028,800. Okay? Now these are all the possible paths. Suppose that I could generate a path every single second. If I could generate a path every single second, then I'm going to divide this by 60, and that would show me what? How long it takes to generate? In terms of seconds. And if I divided it by 60, that would give me the minutes. And then if I divided it by 24, that would give me the days. And I got 42. So it took me 42 days at 1 a second to generate and evaluate and put into a sorting algorithm something like this. 42, what did I say, 42 days? 42 days. Well, what if I could do it more quickly? So for example, let's say I could do it, instead of a second, I could do everything in a millisecond. Then it would take 42 days divided by 1,000, which is 0.042 of a day, which is 0.042 of 24 hours. It would take me 1 hour, 0.80008. So if I could evaluate 1,000 paths per second, it would only take me 1 hour. That means in 1 second I had 1,000. After a minute, I had 60,000 paths evaluated. It's pretty good. So can we do that? How fast would a computer run this program? How many paths do you think it could evaluate in a second? 1,000, like we're doing? More than that, maybe. So maybe a million per second. So we'd have to divide this by 1,000 again, right? So that's more reasonable. So if we divide it by 1,000 again, that gives me only this part of an hour. So times 60, that's how many minutes? Only 6 minutes. So 6 minutes going at 1,000,000 paths per second. So is that a lot of time or is that not a lot of time?
There's a lot of time.
You can argue it's a lot of time. You're going to live that long. Yeah. So it's a lot of time, but it's not a lifetime. So that's good. All right, but what happens if our n is increasing and we try an n, and let's say I'm going to make up an n value, and the n value we're going to try is going to be, it's going to be bigger, but it's not going to be like huge. I'm going to increase it. I'm going to go up to 30. So now what happens is, what increases the most quickly? What increases the most quickly in this case? The number of paths. So if I type 30 factorial, that gives me 2.6525 times 10 to the 32nd power. 32nd power.
Trillion.
Now, a billion is 9, trillion is 12. So this is almost a trillion times almost a trillion. Okay, let's not worry about the details here. So that's how many paths there are. So let's suppose I could calculate 1,000,000 paths per second. So this is the number of paths. If I divide it by 1,000,000, what is that going to give me? If I divide it by 1,000,000, hold on, I'm doing it right. Oh, I screwed up. Okay, what? I got to screw up. I got to do it again. So 30 factorial. Okay, divided by what? Divided by 1,000,000. Somehow I touched a decimal point. Okay, does that look like 1,000,000 to you? All right. He's our million judge. Okay, so if I divide it by 1,000,000, that would. Oh, now I screwed up again. I don't know what's going on with me. Okay. One more time. This is not a hard calculation. I mean, it's for the phone. It's very hard. For me, it's easy. Okay, so I'm going to divide it by 1,000,000. Boom, 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 boom. 1,000,000. He's an expert. Okay, now I have some. Okay, so that's the number of seconds it's going to take me to calculate all those paths. Number of seconds. Okay. So if I divide it by 60, I'm going to get what?
Minutes.
And I divide it by 24, I'm going to get hours. And if I divide it by, what's my next division?
16 to 16 to...
Did I do 24 yet?
Yeah. 16.
Did I do 24 yet? Oh, so now I'm going to divide it by what? 365? What's that going to give me?
Years.
That's going to be days, right? Honestly, I'm very, very upset at myself. Where was I last time? I divided by 60.
Then you do again 60.
Then 60.
Then 24.
I did 24.
And now.
And that gave me days.
Yeah.
So if I divide by 36, it shouldn't give me years.
Years.
Okay, you guys are screwing me up. Okay, it's not bad. It would take 5 years times 10 to the 20th power. If I divide this by 100, that will give me what?
Centuries.
Centuries. Oh, it'll take 5 times 10 to the 18th power centuries. So, but if I speed it up my computer by a little bit, we know it's not going to be very helpful because the complexity is n factorial. Our speed up is linear, but our algorithm is much higher cost, so we're only going to get very, very small amount gain from that. So would you say it's not reasonable to investigate all the possible solutions to 30 factorial size problem?
Yes.
Okay, that is the correct answer. But what if we have that problem and somebody says, okay, well, we have to solve this problem because we need to minimize this distance for 30 and sometimes even 40 or 50. You're like, 50, what? 30, we can't even deal with 30, what about 50? But we have to solve it. So we're going to try to do a different approach, and what I'm going to talk about today is going to be a different way of computing a possible solution. And this is a type of algorithm which we call a genetic algorithm. And a genetic algorithm is an algorithm that tries to find a solution, but doesn't guarantee an optimal solution, which is what an algorithm always does. An algorithm always guarantees an optimal solution. We can prove it, we can show it. It has to find the solution in finite time. But a genetic algorithm tries to find the best solution it can without the guarantee, because it's not looking at a solution from the same standpoint of generating all the possibilities and comparing them. It's trying to do things in a different way. So a genetic algorithm will be something that is from a family of computing ideas called heuristics. Have you guys heard of heuristics? How do you spell heuristic? H-E-U, as long as you know that. Heuristic. And a heuristic basically is, that's interesting. Very nice, very nice. A heuristic is something that tends to produce a solution, but is not guaranteed to produce the solution. Okay, so genetic algorithm is one of the heuristic approaches. There are other approaches, such as fuzzy logic or neural networks. There are different approaches. Genetic algorithms is one of those approaches. They're not algorithmic in trying to get to the root of the problem. They solve it differently, and they may not find the best solution, but let's see what they can do. Because we know that 30 factorial problem is very hard, even if we can solve each instance or a million of them in 1 second. So even a billion of them in 1 second, we still are taking centuries. That's not good. So it doesn't look like if the problem was increased by a lot, it really doesn't matter what our computing power would do, we would not be able to do those problems. Because they would seem to be not solvable, intractable, hard. Hard. Not hard like, oh, it's too hard, my head hurts, but hard like too many possibilities, I can't find them all. Hard. Okay, so genetic algorithms are basically trying to solve solutions to computing problems. Oh, perfect. By trying to mimic what evolution does. And what evolution is trying to do is trying to start. Now think about how man has evolved. A lot of you know that you had parents. And your parents had parents. And your parents had parents. And your parents' parents had parents. And so it just continued on. But at some point in time, we were not exactly the same people we were today. We would like to think that we are improving over time. Although sometimes we can make an argument against that, but by and large, we're definitely improving over time. We're evolving for the good and the bad, but certainly we're becoming taller, stronger, faster, smarter, learning new things. So evolution tries to do that type of a thing. Okay, so it's a branch of AI inspired by the way living things evolve into more successful organisms in nature. So survival of the fittest. Whose thesis is that? Darwin for evolution. Okay. So basically we take something which is a DNA, something that defines us. We are defined by our DNA sequence. Okay? And so our DNA sequence is going to be somehow encoded. Now ours is encoded by, we can decode it by these letters A, C, T, and G. There's a sequence string that defines our DNA. It's a very complex one because there are 4 possibilities, so every single part of our DNA sequence has 4 possibilities. So it's 4 to the power up the length of the sequence. And of course that creates a tremendous number of possibilities. And then what happens is a crossover occurs when one generation of people, we'll call them the parents, produces another generation of people we'll call the children. So we are evolving. So we are here, then our children are here, then our grandchildren are here, and so on and so forth, and this is going on successively. And oftentimes we adapt and we become better at certain things than other things, and if we become better at something, we tend to become more successful. And if we become more successful, then maybe our children become more successful too. And then their children become more successful, and as that spreads, that becomes the more dominant trait, even though initially it might have been an odd thing or something unusual. So the crossover is basically the creation of new individuals through the process of starting the next generation. And of course, as you know, some of you will have a little bit of the traits of your father, and you will have a little bit of traits of your mother. Some combination. Hopefully you get the best of both, but realistically you're going to get a mixture of both, although you may think the other way. But you have a little bit of both. And so that's because some of the encoding of that DNA sequence is similar to, in fact, there is something called the mitochondrial DNA, which is exactly the same. So my mitochondrial DNA is the same as my mother's, is the same as my brother's, is the same as my sister's. And then that's a partial part of the DNA, but the whole DNA is different, but the mitochondrial, that subset of the DNA, is the same. So we get influences. Mutation occurs when something in the sequence changes a little bit. For some strange reason, something just goes wrong or right, and something changes. So that's another part of evolution. Natural selection is that if we have people who are very, very badly adapted to their environment, and people who are okay adapted, and people who are incredibly well adapted, the people who are very well adapted are going to tend to survive. So if we're going to be trying to find a solution to a problem, and we have a bunch of solutions, some of them are going to be very bad, some of them are going to be okay, and some of them are going to be very, very good. Well, the very, very good ones will tend to produce further solutions that may be even better than they were. It doesn't mean that the solutions that are in the middle cannot improve substantially, but we will look to try to find out if we can get some of the better ones to evolve to the best solution to our problem. And maybe the ones that are really horrible solutions, we kind of just leave them. We let them die out. And that's kind of what happens also in the natural selection, is that the people who are very badly adapted, they can't adapt. So they forget to eat and they die. Or something like that. They cannot hunt, they're too slow, they're too lazy. They're on their phone all day, okay? They're not in good shape. They can't hunt the animals for their food. Okay, so I'm going to show you a couple of different things that we can look at. So basically the idea is the most important aspect of genetic algorithms is something called an encoding. An encoding is basically the way we encode a possible solution. If you look at our example here with the genetic algorithm for traveling salesman, you can see that a sequence of, or a permutation of the first 10 integers is a solution to a TSP with 10 cities, or 10 locations. It might not be the optimal solution, but it's a possible solution. We don't know if it's the best or not. So therefore, we could call this sort of an encoding. Okay? Let's say we have a representation of an individual. So individuals are people in a population. So if you had not one of these random vectors of 10, permutations of 10, but you had 1,000 of them, I bet you some of them would be better than others. So if you could rank them by going into the matrix and finding out which one is the best closest, the lowest value, you could pick out of 1,000, you could take the 100 best, the next 100 best, etc. Some of them might be the same value, although they may have different permutations, but you could rank them very easily. Number 1, number 2, number 3, all the way down to number 1,000. And then what you could do is say, well, you know, those bottom 100, they're not showing a lot of promise. So maybe we shouldn't use them. Maybe we should concentrate on the ones that are better. Let's say we want to find an optimal quantity of 3 major ingredients in a recipe: sugar, wine, and sesame oil. We can use the alphabet 1 through 9 to denote the number of ounces of each ingredient, and some possible solutions are 1, 1, 1, and that means 1 ounce of sugar, 1 ounce of wine, 1 ounce of sesame oil. This would be 3, 3, and 1, etc. So that might be a representation, okay? Another example could be the TSP, and we already saw one possible representation. So that would be an individual of a population. Okay, now we need a fitness function. A fitness function is nothing more than an evaluation of one possible solution against another or any other possible solution for a ranking to see which one is better. So we should be able to sort our possible solutions in terms of their goodness or in terms of their fitness. Okay? Now, we have the idea of one population or one generation leading to the next generation, And that's the reproduction methods, and they include mutation and crossover. Mutation is sort of the odd thing that happens when one piece just kind of flips. We could think of a mutation in our TSP population member if we took, for example, random number between 1 to 10, random number between 1 to 10, and switch those two elements. And we would have another permutation. So that could be a mutation. We wouldn't want to do it to 1,000 people, but we might do it to a couple of them just in case that one switch leads to something promising. Maybe it takes a bad member and makes him into a good member. We don't know. Okay, so a mutation is basically a random change in the encoding. So here we can see the individual 123 may be changed to 133, or 123 could go to 323. So what we're doing is switching this one or this one to another random one that's a legal value. Notice that in our recipe encoding, notice that numbers could be anywhere between 1 to 9 or 0 to 9. So therefore there's really 1,000 possibilities. It's 10 times 10 times 10. That's going to be 1,000. Okay, therefore any one location of the 3 could have any one of the 10 values. So we can change any one of them to any other number. Maybe a mutation changes it to a random number. Maybe it changes it by up or down 1 or 2. No more than 2. You define how you want to define a mutation. Okay, the crossover is a way that basically your DNA is received from your parent DNA. So for example, let's say we have individuals 133 and 323. So we'll call this is the mother, this is the father. And so therefore we're going to basically choose a point, sometimes we call the crossover point. So we have to take from this mother and this father to produce a child. And so if we decide, for instance, that we're going to choose a crossover point after the first digit, the above will generate 2 offsprings. So if and that's going to be 3, cross over to 3, 3 from here, and then 1 and cross over to 2, 3 from here. You see how we did that? So we made a crossover point after the first one. So we took the first element from one parent, the other 2 from the other parent, and then we did the opposite from the other 2 parents, the same way. 1 and then 2, 3 from the other parent. Another example is given 2 parents. So one parent is here's the green, or this is actually yellow. Like, oh, I can see green. Did we have a problem with green and yellow before? Yeah. Wow. Okay, this is yellow, that's green. Okay, so now if the crossover point is between the 3rd and 4th digits, 1, 2, 3, 4, you can see what's going to happen here. This is the first 3 from the yellow, the rest from the green. This is the first 3 from the green, the rest from the yellow. Make sense? And so therefore, you can say that these new generation members have characteristics that are sort of a little bit of both of those other parents. They have some of this, but they're different from their parents, but they certainly have a similarity. So this is called a 1-point crossover. So the point would be right between, the point would be right between. Similarly, we could define a 2-point crossover. So if we have a long sequence, we could define a crossover here, go, here we go, mom, dad, mom, dad, or something in between. The rate of crossover is the number of parent pairs, the number of crossover points, and the positions of the crossover points are adjustable parameters. Nobody says that you have to have a crossover point here. There's no rules for this. We're just trying to imitate kind of what evolution is doing. Okay, let's kind of skip around here. So what I want to show you here is, so this is a piece of a code, a program driver, showing you how evolution is going to happen, and then I'm going to show you a program that actually does this type of thing. Okay. So this is just a little main driver, and so it says here we want to evaluate the population. So evaluating the population means that we want to get a fitness for every population member. So if we have 2,000 population members, we're going to get 2,000 numbers associated with each member, or with all the members rather. And then what I'm going to do is I'm going to go and let's say if I sort them, then my TSP member, okay, the best member will be the one which is the first in the sequence, because the sequence will be the whole population. So if I basically take sequence sub 0 and I copy a TSP solution member by the first one, that's going to be the best I have so far. Does that make sense? So just a kind of piece of code. So I'm choosing that one. Now there's some display stuff that doesn't make any difference here. So I'm displaying to a graphics display, essentially, the best member, because that's sequence of 0. Now what I'm going to do is really do the actual evolution. And the evolution basically is going to be based on, I'm going to start with j equal to 0, j less than generation max. So I want to basically evolve my algorithm over the number of generations equal to generation max. Okay, and therefore what I'm going to do is I'm going to just look at the generation counter divided by 100. If the remainder is 0, then output, give me some information about which generation. This is feedback, right? Then what I'm going to do is I'm going to select the population. And selection basically means that I now have them, they are now evaluated. So that means they're in order. So now what I'm going to do is I'm going to say, okay, you know something, the bottom 10%, the bottom 15%, garbage. So what I'm going to do is I'm going to still need the same size population, so I may replicate either the top 15 and replace the bottom 15 with it, or randomly select from the top 25 and fill the bottom 15 with it. I'm going to try to make my population a little bit better than the whole thing by removing the worst X% of it. That's what selection does. Then what I'm going to do is I'm going to do a crossover. And a crossover is going to require for me to sort them by fitness. I'm going to sort them. So let's say I have 1,000 of them. I'm going to start, once I randomize them, what I can do is I can start this counter at 501, start this counter at 1, and then this is going to become mother and father, and I'm going to generate 2 new population members from these two, these two, these two, and I'm going to do this 500 times, producing 1,000 for the next generation. So that's called a crossover. So after crossover, I will then have a new or the next generation. Then before I do anything with them, I'm going to do a mutation. And a mutation means I'm going to do some kind of an odd, random, unexpected change on a very small proportion of individuals to see, because sometimes if I just kind of snap something, it has a chance of getting you out of sort of this uniform commonality, everything kind of being too much the same. So I will do some kind of mutation. So mutation for 1,000, maybe what you're going to do is, if you want a mutation rate to be 1%, that means out of 1,000, 10 individuals are going to have a mutation. So you're going to randomly select a number in your population, choose that one, and make a random mutation. And you're going to do this 10 times out of 1,000. So it's a very small change, but it's a change. Then you're going to evaluate the population. Evaluation of the population means that you're going to, again, find their fitness and then sort them, put them in order. Okay? And so basically what we're going to do is we're going to go up again and continue. And so what's going to happen, we're always going to be, now if refresh is on in my program, then I'm going to say print the best TSP member, because I'm always going to try to generate a best TSP member. And best TSP member will be modified inside here as my program gets better and better. So as program designers, it's up to us to design our encoding. It's up to us to design our crossover function. It's up to us to design the selection function. It's up to us to design the mutation and the fitness evaluation. It's up to us to do that. And then if we do everything correctly, and in light and in the spirit of evolution, we're hoping that our solutions are going to start getting better and better. And how can we know if they're getting better and better? Well, in the case of TSP, they're going to get shorter and shorter cycles around the points. So I'm going to show you our genetic algorithm for TSP. This is a very straightforward program that I wrote, so I'll show you that one. Okay, so this program, this is the tip of the iceberg. So you can see basically, it's got a few classes in it. And this is really, if you can see over here, this is actually very similar to what I just showed you, right? Very similar. Generation max, select, crossover, mutate, evaluate, refresh, blah, blah, blah. Okay, so now I'm able to, this is just a text-based program here in the interface. There's no GUI or anything like that, which is tough. But basically what we have is we have a population size that we can change. we can have a city count that we can change. So for example, so let's say I wanted to do 10 cities. Now what I'm going to do is I'm going to create a 10 city randomly organized within an area of 300. That means that the x and y coordinates are randomly generated between 0 and 300. Okay, and I do this 10 times. I have set a mutation rate at 3.5%. Okay, but I can change that. So just to show you I can change it, let's make it 1.5%, because you can do whatever the heck you want to do. I've also made the generation population size 5,000, but I can change that. I can make the population, for example, 6,000. Okay, with 6,000 I have more ideas. Now, what I did forget to tell you is that in the classical version of genetic algorithms, the initial population is randomly initialized according to your encoding rules. So in the case of TSP, I would randomly start them at random permutations of 10 numbers. And so if I have 6,000 of them, then my probability of getting the best encoding or best solution is going to be 6,000 out of 3.6 million, 8,280 or something like that, whatever it is. So it's not very high. But 5,000 is a little bit lower. How much better is 6,000 versus 5,000? Well, it's better, but still the number is very, very low. Even if I did 10,000, it's going to be pretty low, but it'd be twice as many as 5,000, for example. But 5,000 is very low, 10,000 is still low, but it's better. Still very low. 1,000 over 3.6 million, not very high. Okay, so what happens, of course, to have my best chance of finding a very, very good solution, you would think I would do what with the population size?
Increase it.
Increase it. But the problem with increasing the population size is what?
Computation time.
Then you're slowing down the computation, because basically as you double the population, you have to do double the processing for the next generation. So it's a balance. So for example, I could have 3.6 million, and then if I randomly generate that, I might have the best case. I have the best one. I probably won't, but I might. It's possible. But again, what's going to happen when my number of cities goes to 20, 30, and 40? Then my probability of having the best case, no matter how big the population is, pretty small. So we're hoping that evolution will do what we can't do by simply algorithmically, exhaustingly computing all the possibles. Okay, so what we have right here is we have a setup right now that we have 6,000 as our population. Generation max means that we are going to do this 5,000 times. We're going to do 5,000 populations. So we're simulating how many years? Well, I suppose we're, how many generations? This is 5,000, so 5,000 times, let's say, for humans, our generation is about 20 or 30 years, right? So maybe 100,000 years or something like that, I don't know. At any rate, of course I can increase that also, but if I increase the number of generations, what am I doing? Increasing computation time, because basically what's going to happen is this many times I have to process this many. Each generation is going to be a loop or iteration of these guys, right? So if I increase this to 10,000, it's going to be now 5 million. Things have to happen. Okay, so my city count is 10. Randomly ordered, and we know that's a pretty high complexity. Let's run it and see what this algorithm does randomly doing it. And you can see here is that there's a GUI that's going to show you, and sometimes it freezes, which I don't really like. Let's see, if I minimize and maximize it, it will update itself. So look at that. So that's actually the solution I have right now. Notice that my program is still running, because it doesn't know when it's done, because we don't know what the best solution is. Now, do you think that's the best solution?
Could be.
Could be. We know it's not a horrible solution. We know it's a good solution. Is it the best? Well, that's okay. So now let's try to run. I don't know why it kind of freezes like that. Let's try to run this one more time. Now this time it's going to be a different. Let's see what I can do here. Let's run it. Oh, see, look at those things here. You think that's the best? Okay, again, I'm going to try to see if those were worked out or not, because sometimes, like I said, Okay. Now, this is a different shape. You think that's the best? How many people think it's the best?
Maybe.
How many people think it's the worst? Okay, it's not the worst, all right, so it's still going. But if you think about it, it's pretty quick, right? Fairly quick. All right, so let's make this problem a little bit harder. Now, you know that you don't have to increase this problem much to make it harder. What grows more quickly? Which function? Exponential function or the factorial function? Factorial function. So therefore, if we have a factorial function that's just gone from 10 to 15, that's more than increasing the input of a function. Now you know that in a function is 2 to the n power complexity. If you add one element to it, it doubles the complexity. If you add 2 elements, it what? 4, 8, 16. So this is more than 16 times harder than the previous one, just by adding 5 to it. And I'm only using that as a little omega, because it's actually worse than that. Right? Because I'm comparing using a very simple exponential in 2. Okay, so this is going to be 15, so we're going to get more cities. And what this thing is doing, it's supposed to, I don't know why it's not doing perfectly, but it's supposed to update its GUI every time it finds a better solution. So I'm going to just see whether it's changed it. For some reason, it just doesn't seem to be updating regularly, but it might be. Okay, so this one, okay, so for 15, what do you think? Why is it doing that? I don't know. Let's try to run it again. So now it's going to be different data. No? Okay, what's going on here?
Yeah, it is changing.
It's changing, but then it stops changing. I don't know what it is. Maybe this is some bad program that I fixed that I didn't replace. And for some reason, it's just, you see, it's pretty good, right? It's for 15. So now, remember how complicated 30 was, right? So we're going to try with 30. Now we know 30 was very complex in terms of finding an actual algorithm, even if you could calculate 1,000,000 paths a second. So this is 30. Again, it's the same idea. I'm not going to change anything for now. Let's just run it and see what happens. You can see every time there's a change, it's actually an improvement. This one seems to be changing a little bit better, but so let's see. Could that be the best solution ever? Aren't you amazed how quickly we got that? Compared to the fact that it didn't take us the lifetimes of the universe. It's a lot better. Okay? And yet, but we're not sure if it's the best. Let me just minimize it to see whether it's going to, whether it has updated anything. Let's see if it, look at that, it actually has updated. So this is 30 cities. What do you think? Pretty good solution? So it's amazing that an algorithm, which is not really an algorithm, it doesn't know anything about finding all the possibilities. It's just looking at random data, evolving it through some natural selection, crossover, mutation, etc., can do this. Now let's see what's going to happen if I increase the, so now I'm going to basically increase what am I changing? Mutation rate substantially. So that's going to be a lot more craziness is going to be going on. That may not be a good idea, but we'll try it anyway to see what's happening. So each one of the changes is always an improvement. Only shows if there's an improvement. Until it freezes. Again, I'm going to... You see that one place where it's crossing over? You can actually prove that if there's a crossover, it's not an optimal solution. That's actually a proof. So therefore, this is not the optimal solution. But if we wait long enough, maybe it will fix itself. But the problem is, right, many of the solutions are converging and saying, this is the best solution. So it doesn't know how to get out of it. It doesn't know there's a crossover. It's not that smart. Because it's only comparing against previous solutions, so now let's just see what's going to happen. Let's just see if there's any update at all. There may not be an update at all. No update at all on that. Again, I'm just going to lose. Okay, so now I don't know if this was a problem or not. I don't think so. And every problem is a different problem, because basically all the x and y's are randomly generated. Looks like a pretty good solution. Is it the optimal solution? Can you prove to me that it's not optimal? Well, you probably could do it as a human being. You could probably say, okay, I think if you did this instead of that would be better, and then measure it using the table, and you could show me that maybe this is a better solution. But it'd be hard for you to find the best solution, right, from the get-go. So does that mean we've solved problems that have a super high complexity? Well, it turns out that as we increase the complexity of these problems, if we go, for example, to 40, now what I'm going to do is I'm going to increase the population. I'm going to just crazily increase the population to 60,000 by 10-fold. But I've also increased it from 30 to 40. So I increased that billion-fold. So the chances are I'm not going to do very well. I'm not going to do very well with 40, because 40 is a very hard problem. We'll see what's going to happen. So there's much more work. The number of possibilities, our probabilities are going down substantially. And so people have made a lot of research in the area of genetic algorithms and how to improve genetic algorithms, how to converge onto better solutions, better crossovers, faster convergence. What you can see here is that this is a very hard problem. 40. Now you understand how hard 30 was. Multiply 40, whatever 30 was, by that century complexity that I gave you, and multiply that by 31 times 32 times 33, 34, 35, 36, 37, 38, 39, 40. Now remember, 10 factorial is 3.6 million. So from 30 up to 40, multiplying those numbers probably goes up by many trillions times that other complexity. So you can see that we're not out of the woods for big problems. Let's see if there's anything. Notice that it's working very hard, but notice that it's only done 100 generations. How come? How come only 100 generations are done?
Because the population size has increased.
Population is increased. So basically, 100 populations here, 100 generations here are like 1,000 generations before, because the population is so much bigger. Let's see if we can let it go. There's 200. Not much, right? So we're getting very few improvements. Let's try to decrease the population. Let's go back to, let's do 10,000 and see what happens. And let's just keep it at 40. So this means we're going to get more generations, but it means our probability is lower. We're just going to evolve more quickly. There's 100 already. If you do 40 factorial, you'll see what I'm talking about. Looks like a spider, doesn't it? How many people don't like spiders? You like spiders? You like them? My wife is afraid of spiders. But she's not afraid of snakes. If there's a snake, she's the one that's responsible for taking the snake out of the house. If there's a spider, I'm the one responsible for killing the spider. No matter how large, no matter how small. That's our responsibilities. We take it very seriously. So notice it's still working. When it's working, it's very exciting, right? It's going to show you that they're still going on. And it's 40. So that's a very complex problem. And we're close. Look at this. That's a nice. That looks like a horse.
Well, a very big head.
Yeah.
2 heads. And a tail. See, random data can give you very nice images. All right, so what do you think? You think it's interesting? So that's pretty good. All right, so, yes, so genetic algorithms are very, very interesting. I've actually done some work and I created some genetic algorithms. So instead of running one genetic algorithm over the same data set, I can actually create 8 or 4 or 16 of them. They run, they have different random data, and then they communicate and they try to converge a little quicker into things. But there's a lot of people are doing some interesting things in genetic algorithms. So you can see that sometimes you get lucky and sometimes you don't get lucky. Sometimes the data is just inherently harder to do. What would be very interesting is that we could actually plot points if they were exactly on a circle to see how difficult that would be. Would that be a hard problem? Would that be an easy problem? It's easy for humans. How would it work for a computer that doesn't have any vision? Just looking at it from the standpoint of X, Y values. Okay, so that's our talk for today. I'm going to let you guys go. You are free to leave.